Okay. So now we are here. Here we are. Okay, good. Third day today. So we continue our exploration of what are the recent developments in the Swampland program. And as I told you already in the first day, there's a lot that has happened recently related to the idea that there's no global symmetries. Okay, so today we're gonna see we're gonna the past couple of days we learned about the relationship to completeness hypothesis and application of no global symmetries to generalize global symmetries, and how that led us to conclude that there are charged states in the theory, which goes under the name of completeness principle. And today we're going to take a bit of a turn, and we're going to describe an application of the idea of no global symmetries conjecture, which is very gravitational, has to do with space-time itself. Okay. So that's the covariance conjecture. And very recently, the covariance conjecture has been used to argue that, in some sense, string theory is the only theory of gravity, also in 9 and 8 dimensions. So yesterday, we saw that was the case in 10 dimensions. Today, we're going to extend that to 9 and 8 dimensions, which is pretty recent result. So you see, we're getting closer to 4. Okay, before I get on with the lectures, a couple of things. I have a problem with my laptop, which is how you see my face via the camera in my laptop. So probably that's gonna stop working at some time. Like the lecture should still be fine because I'm using my iPad's microphone and so it should be fine. But I apologize for that because you're gonna stop seeing my face at some point. And so that's one thing. Another thing, somebody yesterday asked. So yesterday we were talking about the global form of the standard model gauge group. And whether we could see the ideas of completeness, can we see any of that really experimentally? And I mentioned there was a paper which I didn't remember at the time. Let me just put this here. Good. There's a paper I didn't remember at the time, which had something to say. Is this paper? 02823 by Agrawal et al. Where they actually consider actually consider the standard model coupled to a QCD action. So they have an action, some additional scalar. So standard model plus action. And according to the completeness principle, this action has some strings. These strings are produced during cosmology, and they form like a network of patches. And so what these strings can do is that if you have a source of light, distant source of light, and goes through these patches, the polarization of the light depends on the path. And so that's an effect that we can measure. And which possible angles of polarization you can have depends on this global form of the standard model gauge group that I was describing yesterday. So this is a paper, actually, it's a Fino paper that uses completeness twice. Uses it first to conclude that there's action strings, as we did for string theory in 10 dimensions. And second, it uses it again to relate the polarization angles that you get so if there's light flashing from the object, light is supposed to be yellow. So if there's light flashing to the object, the two different paths that the light follows, you get different polarizations, and that's related to the global form of the standard model gauge group. Okay, so this is a very concrete way in which phenomenological people, these people are phenomenologists, are looking for signatures very much related to the objects that you predict in the swamp. Okay. Okay, so yeah, this is something I wanted to mention from yesterday. Are there any questions about this thing? It's not really part of the lectures, but if there's any quick questions, maybe I can take it now. That's the other thing I wanted to say. You guys have been doing very well these past 2 days. Keep it up. Keep asking questions, okay? Okay, so now let's get going and let's start talking about the covariance conjecture. Okay,
sorry,
so what is the covariance? Please, is there...
Your voice is noisy a little bit for me. I'm not sure if the problem is with, I mean, in my side. So maybe I should ask.
Does anybody else have the same problem? Can anybody else tell us if they have the same problem? Does everybody else, if you're hearing me all right, please raise your hand.
Yeah.
No, the voice is okay.
Okay, so the problem is on my side. Okay.
I'm sorry to hear that. I mean,
Okay. No, I will resolve it. Thank you very much. Okay. Sorry for interruption.
no. Thanks. I'm a bit worried because of this thing with the laptop. So, yeah. Okay. Very good. Very good. Okay, let's get going. So there's this no global symmetries idea that we discussed. There's no global symmetries in quantum gravity, and we think it applies to ordinary symmetries, bills of local operators. We also think it applies to generalized symmetries involving extended operators. And now we're going to see that it can also apply to symmetries, new kind of symmetries built out of space-time topology. Itself. To discuss this, first I need to explain to you what do I mean when I say that that you can build symmetries out of space-time topology. What does that mean? Well, in a theory of gravity, so in gravity, in a quantum theory of gravity, it's very natural to imagine that the distance or metric between 2 points fluctuates due to quantum mechanics. I think this is one of the things that it's completely independent of whether you have string theory or not. Everybody agrees that distance fluctuates. And why is that? Well, how do you compute the distance? Suppose I have 2 points, P1, P2. If I want to compute the distance between P1 and P2, how do I do that? Well, I do the integral of the square root of, I pick some curve, perhaps the geodesic, should be the geodesic, and I compute this thing. Okay. And classically, this is well defined, but quantum mechanically, this thing is an operator. So I should put an expectation value here, and I have something like the expectation value of the distance. But naturally, there's going to be fluctuations for the distance. Okay. So if I measure the distance between these 2 points, sometimes we'll get one answer, sometimes I'll get a slightly different answer. Okay. I think that's very natural from the point of view of just gravity, that the distance between things fluctuates, because after all, the whole point is to make the metric dynamical. But if we're making the metric dynamical, why not make the topology dynamical? What do I mean by that? Okay. Imagine that I have a region of space, and in this region of space, I draw a loop. Okay. And then I ask the question, can this loop be contracted to a point? Okay. It's not as well-defined a physical observable as the one I had before, but it serves to illustrate the point. Can I contract the loop to a point? Well, the way I drew it, certainly, right? I can just take the loop and shrink it. Oops. And shrink it. And shrink it to a point, right? So at some point, it just becomes a point. However, imagine that I'm telling you that the topology of space-time can fluctuate, so that sometimes space-time will look like this, sometimes like this. But sometimes there can be a quantum fluctuation, and it will look like that. So it can grow like a handle connected to this thing, sometimes like that. Then the physical question I was asking is whether can this loop be contractible? Well, if a hole grows here, it's really not contractible anymore, right? So the answer to topological questions such as, is this big loop that I'm drawing contractible, can depend, can have fluctuations, can depend on one can imagine a theory of gravity. One can imagine that topology fluctuates, and the answers to questions such that such the one I'm just asking, which involves topology, can also fluctuate. This idea is actually very old, has nothing to do with string theory. So already Wheeler was talking about the quantum phone, which is the picture that at very tiny length scales, at scales close to the length scale of space-time, is continuously fluctuating. It's not just the metric that is changing, it's also the topology. But unlike metric fluctuations, unlike metric situations, it is not obvious at all that topology fluctuates. Okay, so I'm telling you, I just told you a consistent story that makes sense, where I just shown, well, maybe topology fluctuates, and if topology fluctuates, the answers to questions like, is the loop contractible, really depend on, it can really change. But maybe someone can come and say, well, I don't think this is happening. I think the topology of space-time is frozen and it cannot change. Okay, and a priori, this is a very reasonable position. And I would say 40 years ago, perhaps people didn't really know if topology fluctuation was a thing. Nowadays, we have much better evidence, which I'm about to describe. So why do we believe topology fluctuates? Well, there's 3 reasons. There's evidence from string theory, which I will describe. In string theory, topology certainly fluctuates. Then there's holography, what is called the ADS-CFT correspondence. And quite related to this, so I'm calling it 3, but I could call it 2B, is Euclidean quantum gravity. Okay, so I'm going to describe these 3 bits of evidence to convince you that topology fluctuates, and then I'm going to explain how the fact that topology fluctuates has very interesting consequences for global signatures. But before I do that, is there any question about the general setup, like the general idea that topology fluctuates? Are there any questions?
Sorry, Miguel. What is the origin of the fluctuation? It's again the quantum effects, or? Yes,
that's exactly right. That's the idea. It's quantum mechanics. It's in principle quantum mechanics. So I'm going to make that more precise in the ADS-CFT example. But yeah, it's quantum fluctuations. So okay, okay, good. My computer's battery is dying, and so what that means is that I won't be able to, because I'm sharing screen with the iPad, I won't be able to see if anybody's raising hand. So if you want to ask questions today, please just unmute yourselves and start speaking. Or I mean, if you see somebody raising hand, I mean, can you please let me know?
Yeah.
Okay, thank you. Excellent, because I'm not going to be able to see. I'm sorry about that. Okay, so Euclidean quantum gravity. Okay, why do we believe topology fluctuates? Because these things. Okay, so what is the evidence coming from string theory? Well, in string theory, you have topology fluctuation all the time. For instance, when you compute string scattering diagrams, what you have is just you compute how 2 strings scatter. You do things like, for instance, this is a 2-to-2 string scattering. You draw a diagram like that, and there's an amplitude associated to this, but you also need to include loops. And the way loops look like in string theory, right, is you add perhaps a handle to this thing. You draw a hole in there, or 2 loops, 2 holes. So this is another amplitude, and you need to add all of them together. So you really need to take into account topology fluctuation in quantum gravity in string theory, we're computing string amplitudes. The worksheet is itself behaving as a quantum theory of gravity, but you might say this is not the same as fluctuations topology in spacetime. So one thing that you can say from the point of view of string theory is that string theory in some circumstances is completely smooth, even when we change topology. Okay, so an example of this, it's you can read in Brian Green's book, also in his lecture notes online, is the conifold. What's the conifold? The conifold is a geometry that appears in string compactification. So string theory, you sometimes you need to compactify 6 dimensions, right? To get you need to compactify from 10 dimensions to 6 dimensions. And sometimes the manifold you compactify, which is called descarabillado, can develop a singularity. Okay, can develop some point which looks very spiky. And the conifold is a model of the singularity. So locally, you can describe by an equation. Okay, so for instance, a conifold, this region is locally described by an equation like this. Where these 4 coordinates are complex. So this is an equation in C4. And this is a higher dimensional version of a singularity like this you can have in the plane, for instance. So if you have, for instance, if you draw a coordinate system, x and y, and you write the equation x squared equals y squared, you get something like this. Okay, so something with it looks like a bit like a double cone, which is why this thing is called a conifold. Now, this equation you can deform in 2 different ways. Okay, you can deform it like this. Okay, that corresponds to a certain definition of the equation, or you can deform it like that. When you do this, for this picture I drew on the plane, the two deformations look the same. One of them is just the rotation of the other. But when you do in the conifold, when you do this kind of, there's similar deformations in the conifold. The similar deformations in the conifold change topology. Okay, so the usual picture that one draws for the conifold is, so the conifold one can show is a product of it's a cone with this base. So it's a 2-sphere times a 3-sphere, and people sometimes draw like this. So this is the conifold. So this is S2 and this is S3, and you can deform it like this. So you make the S2 have finite size, so the S2 has no finite size, and the S3 still goes to a point at the tip of the cone. Or you could deform in a different way. You could deform, you could deform in the other way. You could deform like this. So that the S3 has finite size, but the S2 still shrinks at the tip. This is just a pictorial way that is commonly used to describe the conifold. The basic point I want to emphasize here is that when you do this change in topology that happens in the conifold transition, the low energy effectively theory that describes this in string theory is completely smooth. Okay, everything is actually this kind of transitions. One of them is described by a Higgs mechanism in the effective field theory, and in the other one, it's just some fields becoming massive, some other fields. So it's completely smooth. So here's a situation in string theory where, there's topology changing and the theory is completely smooth. And furthermore, the parameters that control whether you deform in this way or that way, so the parameters that control the formation, are protected by supersymmetry. So, somebody could tell could say, well, maybe you can make these drawings, but how do you make quantitative? You can change topology. The reason why you can do that, okay, is precisely because these parameters are moduli and they're protected by supersymmetry. So there's no way you can get away with that. Okay. Any questions about the conical? My camera just died out, so if you're asking questions, please just unmute yourself, or if you cannot, please just write on the chat so that I mean can tell me. Okay, so there's a lot of evidence coming from string theory that you can change topology, and there's also evidence for this coming from, which I think is it's very convincing, coming from all over, from the ADS CFT correspondence. So what is the ADS CFT correspondence for those of you that might not be familiar? ADS CFT correspondence is a framework that completely captures any quantum theory of gravity which lives in ADS space. So this is space with a negative cosmological constant. And the nice thing about it, so spaces with negative cosmological constant, you can draw like that. They have a boundary. And so in the ADS space, there's quantum gravity. And it's described in terms of a field theory without gravity, which lives on the boundary. Okay, so the ADS-CFT correspondence is extremely powerful. It allows you to trade questions about quantum gravity to properties of the CFT and vice versa. The CFTs that one needs to use in the ADS-CFT correspondence, there are CFTs which have a large number of degrees of freedom. Okay, and the properties of the properties of the partition function, okay, of the CFT, one can compute the partition function of the CFT, which is just putting the CFT at finite temperature. Okay, and properties of this partition function match the properties of the ADS side. And the way one is supposed to compute the partition function on the side is as a sum of saddles contributing to the bulk path integral on the ADS. Okay, and these saddles, it's very important to include all saddles to get agreement with the CFT. We know examples where this doesn't happen if you do it like this. And these saddles involve contributions of different topology. Okay, so for instance, to compute the partition function at finite temperature, we need to include two saddles. One of them is what we call empty ADS space. So that's ADS with nothing inside. And another contribution we need to include is ADS with a Euclidean black hole. The topology of these two solutions is very different. Okay, so the topology of this one is a circle times a ball. Okay, and the other one is an S2 as a two-sphere times a disk. In the boundary, they look similar, but in the bulk, they are very different. Okay, the basic point that I'm making here is that this is a very well-established framework for understanding quantum gravity in spaces with negative cosmological constant. It's very precise. It's by far the most precise framework that we have for understanding quantum gravity. The only problem is, of course, that it only works with spaces with negative cosmological constant. And for it to work, it really requires sums over different topologies. So really, ADS-CFT is telling you that topology can fluctuate. Okay. And the third point that I was putting forth as evidence that topology fluctuates is really a variant of this, that there's calculations, what I was calling Euclidean quantum gravities, similar calculations. Also in flat space. require some sort of topologies. Is there a question? Is there a question?
No question at the moment.
Oh, sorry. I just heard somebody muted, and I thought it was
okay.
Okay.
There is a question. Yeah, Reza, please.
Excuse me.
Yes, please.
In your early discussion about topology fluctuations,
Yes.
shouldn't one take into account the restriction from the topological invariants made from the metric, restriction from that on the topology changes? I mean,
Wow,
fluctuation of metric and the topology are somehow related together.
Yes. That is an excellent point, and in fact, this is what I'm going to be talking about next. Yes. So I'm sorry I didn't, because I cannot see the Zoom chat right now. I don't know who asked, but whoever asked, this is a very good point indeed. So what I'm describing is just abstractly there can be topology change, but which topology change in particular, which saddles are included, which saddles are excluded, is the question we're going to be discussing next, and it's a very important question. You're completely right. This is what I'm going to be describing next. Okay.
Thank you.
Any other questions about the topology change in general? Let me just say that what you asked, really, like, there's topological invariants that are invariant even after doing topology change transitions. It's precisely the reason why this is interesting for the Swampland program. It's precisely the reason why I'm giving this talk at all, actually. So it's a very good point. And any other questions? Okay, so wait, so what, so yeah, so why is this interesting for the Swampland? It's precisely because there are topological invariants that associated to non-trivial topologies that are protected from topology change, and these topological invariants are global symmetries, in a sense that I make precise symmetry global. Okay, so some topologies are protected from change, and that is bad for quantum gravity. And imposing that is bad, we're going to learn new things, and that's the covert distance conjecture. Okay, so let me first explain that even though there can be some topologies that are protected, in fact, most topologies are completely fine and do not lead to invariance in quantum gravity. So suppose you have a handle like the one I was drawing before. So you have a handle like that. Okay. Now, in principle, this is not a problem. It cannot. So what is a global symmetry? A global symmetry is a conserved charge. It's something that I cannot get rid of. Okay. And if I allow myself to do topology change, well, anything that I can write down, maybe I can also undo with topology change. So for instance, if you have something like this, I could try to just make the throat very thin at some point. I can try to get rid of the handle that I drew by doing something like this. So I make it like that. Then from here, I actually break it at the neck. So I actually split it. This is something you can do smoothly. So you end up having two things like this. Okay. And once you have two things like this, these things are locally like flat space. So you go back to flat space. So a topology like this handle, okay, topology like this handle is not going to lead to any, so topologies like this are not going to lead to global symmetries. Okay. However, there's different kinds of topologies that can actually there are other topologies. You cannot kill so easily. So Actually, unfortunately, to find the first example of something like this, which is not so easy to kill, you either need to look at very subtle things involving fermions, or what we can do is you need to go to 4 dimensions. Okay, so actually to 4 spatial dimensions. So that means, so let's go to space-time dimension d bigger than or equal to 5. Okay, and in particular, let's take it for concreteness. Let's just take it to be 5. Okay, let's say that the dimension is 5, and let's imagine that we have a constant time surface. And this is, it's just locally R4. So to this R4, I am going to change it. And I am going to glue a certain object to it. I'm just going to glue it like this via a tube to certain compact manifold that I like very much, which is going to be the main character. This compact manifold is a particular manifold which is called K3. Okay, so this is a K3 manifold. So what is the K3 manifold? It's a particular manifold. It has to be this manifold. It can be defined in several ways. So, for instance, you can define it as a complete intersection in projective space. So, one way to define it is like this, but that won't matter very much for us. Okay. If the set of solutions of this equation is set to 0, where Z1, Z2, C3, and C4 leave their coordinates in complex projective 4-dimensional space. Okay, so that means that this guy is equivalent to lambda C1, Z2, C3, C4 for lambda in the complex numbers -0. Okay. So that's just a way to define this guy. You can check that this is a complex 2-dimensional space. So why is it complex 2-dimensional? Well, this is a complex equation, has 2 variables. So it imposes 2 constraints, and the ambient space looks like it has 4 complex conditions. Has 4 complex dimensions, but because of the identification here, you lose 1 complex dimension. So actually, it's a 3-dimensional complex space. You put 1 complex equation that gives you a complex 2-dimensional space. So this K3 guy has dimension 4. Okay, so a 4-dimensional object. Okay. Now, why do we care about this guy? Well, there's many interesting things about K3. In string theory, we love to compactify in K3. In a sense, it's something like a Calabi-Yau twofold. It's a 2-dimensional version of Calabi-Yau's. But really, the thing that interests me about K3 right now is that it has a very interesting property. Suppose you choose a metric on K3. Any metric. It is a compact manifold, so you can put whatever metric you like. Maybe you like a metric which connects to a tube to R4 or whatever. You put any metric you like. Okay. And you now compute the following number. You integrate over all of K3 this thing which I call P1, the first pointer in class, which is just defined like this. It's just some differential form which you construct out of the Riemann tensor. Is R nu rho sigma R mu kappa lambda. So this brackets means that you are antisymmetric in these 2 indices. So this is a 4. It's a completely antisymmetric tensor. Okay, and you integrate it on K3. Okay, and here's the interesting thing. You would guess that the result of this depends on the metric, because the P1 explicitly depends on the metric. And so and it's true that this object depends on the metric, but its integral doesn't. The integral of this guy, no matter which metric you put on K3, it's always 48. It's a topological invariant. Okay. This is one of the topological invariants that the person who asked the question before was talking about. Okay. it's a topological invariant. And furthermore, it's a topological invariant that cannot be changed by topology changing transition. Okay, so how do I argue for this? Well, it turns out that there is a very general mathematical framework that allows you to understand all of this topology, any possible topology changing transition in a unified way. And that framework is called covariance theory. So what's the relationship of covariance theory with topology change? Well, suppose you have some manifold with some topology. Maybe this is the K3 I was talking about, something else. And suppose that there's some topology change going on. So what does topology change mean? Topology change means that some handles grow and reattach in different ways. And so I'm gonna draw as a movie, if you would, with time in the horizontal axis, what happens to this manifold under a general topology changing process. At the end of it, it becomes some other manifold which has different number of handles. Topology of it could be very different. And the way I can draw it like that is by saying the two manifolds are the starting point and the end point are the boundaries of one manifold in one dimension more, which itself has non-trivial topology and describes the topology changing process. Okay? So a topology changing process in general between manifolds M1 and M2 is described by another manifold B such that the boundary of B is the union of M1 and M2 with opposite orientation. Okay. This is the general description of topology change. And it's what mathematicians call a cobordism between manifolds M1 and M2. Okay. Anything that is a cobordism invariant, which is cobordism invariant. Okay, so anything that's a cobordism invariant, meaning that it doesn't change under cobordisms, is invariant under topology change in quantum gravity. This number n here is an example of that, and the P1 is a cobordism invariant, and so provides an example of a global symmetry in quantum gravity. So this symmetry in this particular case is just counting the number of K3s. So for instance, if I have R4 and I glue one K3 here and another K3 here and another K3 here, and I compute the integral of P1, this is gonna be 48 times the number of K3 that I put, so it's 48 times 3. If I put n K3s, put n, is gonna be just 48 times n. Okay, so this is a global symmetry. It's just a conserved charge. It's conserved by topology changing processes, and so it's a global symmetry in gravity. And anything that is a cobordism invariant is gonna give you a global symmetry. So to understand what are the possible global symmetries that you can get from this kind of picture, you need to understand what are all the possible cobordism invariants. So I'm now gonna explain what the cobordism conjecture is, and I'm gonna tell you a bit more about cobordisms. But before I do that, are there any questions about this general picture? So the core idea in this lecture is this one, is that topology change, a topology change in transition can be described in terms of a cobordism, okay? And the things that cannot be changed by cobordisms are actually global symmetries of the theory. Are there any questions about this? About the topological invariant or about the cobordism picture?
If you start with a R4 which has 2 K3 and then end up with R4 with 3 K3, then
That's
What's
great. You
the-
cannot. That's the thing. You cannot do that. Okay. So here. What I mean is the following. Okay. This is exactly the question.
So, but what's
suppose,
the point with topology change?
So here's the thing.
can,
Please go ahead. Sorry.
no, I can't see the point with topology change. What does it mean? If you cannot change the number of K3s.
The point is that there's many different things that you can do with topology change. Okay. You can, for instance, you can get rid of handles or something like that. So most topologies are actually not giving you not giving you topology change. Okay. Sorry, most topology changing processes are not giving you global symmetries. There's a few, like the number of K3s that you cannot change with this coverdism. So what happens, like, okay, if you try to do that, so you have one K3 here and one K3 here. Let's say we want to go to one K3 only. Okay, that would be a topology changing process. That would be a that would be something that would violate the conservation of this number. Okay, what happens is if you try to construct a manifold like this, you find that such a manifold does not exist. Okay, so there's no manifold that will do the trick. However, and this is actually the point when I'm going to be discussing next, you can actually get away with this. You can do something like that if you allow certain singularities. Okay, so with certain singularities, you can actually also kill this global symmetry. So the whole point of this discussion is that in any theory of gravity where the topology change is allowed, this looks like a global symmetry. But now if you impose the Swampland principle that there's no global symmetries, this is telling you that on top of the classical smooth geometries that you always have in supergravity, you must also include configurations with singularities like this, which allow you to break the symmetry. Knowing that you can include the singularities is new information that you don't get from supergravity. It's purely Swampland information. And it's basically telling you there's new singularities. There's singularities you can include in your quantum theory of gravity, which you can actually use to prove string universality in certain cases, as I will do later. Did I answer your question?
Yeah.
Okay.
I see.
Okay, good. So okay, good. So yeah. So let me just then try to give you what's the general framework for doing all of this. Okay. So these coverdisms. Okay.
Excuse me.
Yes. Any question? Yeah.
May I ask you a question?
Please.
May you please say how these global symmetries are accommodated in this topology change story?
How are these global symmetries accommodating in topology change story?
Yeah, how they are related? How they are related to the topology change of the manifold? I didn't get the point.
So right. So the basic point I'm making is there's if you allow for different topologies, okay. So if you allow for topology change, okay, in principle there's nothing preventing you from considering configurations where you glue basically any topology you like for instance this K3 to R4, okay. But if you allow for topology change, you also need to, and so it looks like once you put one of these topologies, you cannot get rid of it. You cannot completely deform it away to the vacuum. If you cannot deform it away to the vacuum, it looks like a global symmetry. That's the global symmetry. So far, so good?
By a global symmetry, you mean a transformation that changes one topology to the other?
No. So no. What I mean, the only thing I mean is that if I can glue a topology, okay. So the way I'm thinking about this is, I am just gluing K3 to R4 here, and it looks like a localized object in R4, looks like a particle, okay? So far away, if you're an observer far away from it, looks like a particle, it's just some blob, okay? And so if a particle has a conserved charge, okay, that means that you cannot deform it to the vacuum. So the question of whether this blob that I created here, this K3 carries a conserved charge or not, is the question of whether can I deform it smoothly to the vacuum or not? Okay. To do that, I'm gonna need for sure topology change. And sometimes when I have topology change like this, if instead of having a K3, I have something like this, I just drew here, how can I smoothly deform it to the vacuum? Okay, I just detach it like this and it smoothly deforms to the vacuum. So an observer far away from here is gonna look at this object and say, oh, it looks like an object, but look, the object is this, so the observer is here, the object is disappearing. So it's disappearing into the vacuum. So it really carries no global, there's no conserved charge associated to it. There's no global symmetry. Global symmetry is associated to conserved charge, okay? So there's no conserved charge. What I'm telling you is that this K3 guy is different. For this K3 guy, there's no way that you can deform this away to the vacuum. Okay, and so in smooth supergravity, and so it looks like a conserved charge. The number of K3 particles, you could call this a K3 particle. Number of K3 particles is conserved, apparently. Okay, did I answer your question?
Yes, thank you. Thank you.
Okay. Yeah, thanks for the questions. This is great. It's very important.
Sorry, one question.
Please.
How do you get rid of that handle in your first example?
In the first, oh yeah, it's just good. So I'm just deforming. So actually, when I was drawing here, okay, it's really just the cobordism. I'm just making the handle very thin and then detaching it. Okay, and then you can do it in a smooth way. You're not creating high curvatures.
But it's like a handle on a sphere. But how can you get rid of that handle in a smooth way? I can't see it.
Right. So what I mean is, right. So you can have a situation where you have the that's sorry?
Like a handle on a sphere. Okay, it's like a handle on a sphere.
Mm-hmm.
How can you get it? It's a topological invariant. It's the hole that you have.
No, but this is not invariant under cobordisms. Okay, so the point is that this guy is the boundary of a manifold, which on the other side only has a sphere. Okay, so the handle does it just drops like that. So I think the better way to see it is like this. It just pinches off like that. That can be a smooth thing if you add one dimension more. Okay, so you maybe are thinking that this is not smooth because it looks like this at the separation point. Is that the point?
No, I'm thinking because it's a topological invariant, the number of holes on the sphere. Okay, we know this is that the number of holes or number of handles are invariant under smooth deformations.
Yeah, it's smooth deformations, but not cobordisms.
Mm-hmm.
Okay, a smooth deformation, right? I agree. A smooth deformation is like a diffeomorphism. It's not. It's right. So if you do not allow for topology changing processes, the number of handles cannot change. That I completely agree with.
Yeah.
But I'm allowing for topology changing processes that involve smooth geometries, and the way I'm quantifying that is via cobordism. Okay. So the number of the genus of a surface is not a cobordism invariant. That's the mathematical statement I'm talking about. Okay.
Okay.
Yeah. Thanks. Okay. So the cobordism that I'm describing here has very interesting properties. So first of all, it's an equivalence relation between manifolds. Okay, so if M1 and M2 are joined together like that, like I draw here, they're equivalent under cobordism. And furthermore, this equivalence relation carries the structure of an abelian group. Okay, so the set of equivalence classes, you can take the set of equivalence classes of manifolds which are invariant to cobordisms, and they form an abelian group, which is called the cobordism group. Okay, and in every, so these cobordism groups, they're called omega. So for instance, the cobordism group of four-dimensional oriented manifolds is Z. Okay, which means that you can group together every manifold, every four-dimensional manifold, oriented manifold is cobordant to in this case. So for instance, if you allow me to introduce spin structure, which is something I like to do because I like to talk about theories with fermions, then this four-dimensional group is Z and is generated by K3. Okay, so the different classes of this cobordism group are precisely the compactifications with a number of K3s. So this integer n, which is the integral of P1, corresponds precisely to this Z factor. Okay, what this means is that every four manifold, to be more concrete, every four manifold, every spin for manifold is cobordant to a disconnected sum of n K3s for some n. Okay, and this n is precisely the generator of the C factor here. So when I was describing about the K3s, it's precisely captured by this cobordism group. Okay, so the cobordism, so the bottom line is that in any theory, in any quantum theory of gravity, if there is a non-vanishing cobordism group, there is a global symmetry. Now, cobordism groups themselves can be, there's different cobordism groups depending on the structure you introduce in the theory. So for instance, these guys, these are called the oriented bordism. It's just theories of manifolds with an orientation. The one I drew before are the groups you need to use in theories which include fermions, because fermions, for fermions to be consistent in when you compactify on a general manifold, they must have what we call the spin structure. So these are different bordism groups, and more generally, you can have bordism groups with any structure S. So, for instance, if you're compactifying on a theory which also has U1 gauge fields and spin fields, and fermions, then you compactify on spin U1 bordism groups, something like that. Okay, and what this means is that if you have some structure S, like gauge fields or spinners or you name it, in the bordism that I drew here, the extra requirement you get is that the structure here S that you have here on both initial and final manifolds is also preserved to the middle manifold. Okay, so depending on which quantum gravity theory you're looking at, you're going to have different bordism groups. But whenever there's a bordism group, there's a global symmetry. Okay, so what that means is that if there is a bordism group with some structure S, which is non-zero, there's a global symmetry. What that means is that one, as I was saying before, one must add additional geometries, additional singular geometries that destroy the global symmetry. So for instance, what I mean, to be more concrete, in the case that I have about K3, this is the K3 again, it's impossible to write K3 as the boundary of another manifold because of the cobordism charge I was describing. So this is impossible, but maybe one thing that one can do, in fact, one can do, is to close off and put a certain kind of singularity here. This is not going to be anything you can describe in smooth supergravity, the principle that there's no global symmetries is telling you that these objects must exist. And once you include these objects, you have an improved covariance group, which is, in this case, it becomes 0 because you just kill the only class. So it goes from C, which is what it was before. After introduction of these defects, it becomes 0. So that lets me finally write down what is the covariance conjecture, which is the main result that I wanted to tell you about, and I guess I'll tell you the next day about applications. But that's the covariance conjecture. It's just an application. There's no global symmetry in quantum gravity, and it's telling you that omega, the covariance groups of quantum gravity, meaning once you introduce, what that means is once you introduce all these defects, the covariance groups of quantum gravity are actually 0. That's just saying that there's no global symmetries. Okay, so that's the basic statement, and the reason why topology change has any relevance to the Swampland program. The introduction of topology change creates new global symmetries, which you then use Swampland principles to predict singularities that kill them. So that's the general idea. Now I'm gonna describe, perhaps in 2 minutes, a very cool application of this, but perhaps I can take questions first about covariance conjecture. Any questions, please?
So this is actually rephrasing the statement that there is no global symmetry in quantum gravity. Right?
That is completely correct. It's even a particular case, okay? Because as we discussed in the other lectures, there's no global symmetries involving generalized global symmetries or all the kinds. This is just for this particular symmetries that you associate to topology change. Okay.
Right. I see.
Mm-hmm. Okay. Any other questions? So I should mention, by the way, that this is from a paper. This paper has been very influential. So the covariance conjecture and thinking about this way has sort of like started a mini revolution, I would say, in string theory or in Swampland. And this is a paper by McNamara and Baffa from late 2019. Okay. So in the 2 minutes that I have left, perhaps, I mean, do I get 2 minutes?
Yeah, sure.
Okay. So I'm gonna, what is the most interesting thing that you can do with any Swampland conjecture? Well, you try to apply it to the real world. Okay. Then let's compute covariance groups. What are the covariance groups of the real world? Okay. So you need covariance groups with a structure which is spin, but also takes into account the gauge groups of the standard model. So SU3, SU2, U1 in a certain way. Okay, you need to compute these guys. And so for different values. So for instance, omega. So let me start with first of all, you don't compute covariance groups all the way to the dimension of space because you're talking about localized objects. And so it should have less dimension of space. So the first one that you consider is omega-3, which for this case, it vanishes. So this would be describing particles, okay? I should say that for instance, the way I introduce it here, these K3s in 5 dimensions, for instance, would be if I'm introducing these K3s in a 5-dimensional theory of gravity, they look like particles. But if I'm introducing them into, let's say, a 6-dimensional theory of gravity, they look like strings. In a 7-dimensional theory of gravity, they look like membranes. So the objects that you construct by this topology change have different dimensions depending on the relative dimension of the degree of the covariance group that one is looking at and the dimension of space. So omega-3 in 4 dimensions will create particles. sorry, no, the objects that you could predict for the correlation conjecture here are instantons. Omega 2 has an omega 1 are Z2, Z2 plus a Z factor. This Z factor, the defects that kill it are particles, and it's associated to magnetic charge. So in particular, this part of the covariance conjecture is predicting monopoles. We already got monopoles from the arguments in the other lecture using generalized global symmetries, but this is an interesting. What we are just checking out what we get is consistent, and these other Z2 classes are actually related to a prediction of a very interesting object. It's actually a string. We are predicting a string in the standard model, and it's a very special string we call the spin defect. And what defines the spin defect is like, so I'm just drawing the string in space-time. As you go around the string, particles which are bosonic don't get, nothing happens to them, but a fermion picks a -1. Okay, so it's a particle, it's a string that provides an action to -1 to the F as you go around. Okay. So this is a new object that one is predicting from covariance conjecture is there in the standard model. And finally, just to finish, and I'm gonna start the lecture tomorrow explaining this more quickly. You can keep going. I did omega 3, omega 2, and omega 1. But one can also look at omega 0. And omega 0 for the standard model is C. What does that mean? What is the defect that kills this? Well, for omega 2, it was a particle. For omega 1, it was a string. So for omega 0 is a membrane, but not just any kind of membrane. It's what we call an end of the world brane. So this is the universe. And at some point you hit a wall. And this is the end of the world brane. Okay, so covariance conjecture is predicting from this point of view that the universe admits a boundary. This is not saying that when we go out in the universe, we're going to see such a boundary. It's really saying that such an object is a valid solution and in principle could be created according to Swampland principles. And in fact, covariance conjecture is telling you that every quantum gravity admits what one might call a boundary condition, meaning an end of the world brane, meaning an end of the universe. Okay, so covariance conjecture is in a sense predicts that every universe can end. Any consistent quantum gravity model admits a boundary conditions, admits an end of the universe. And just to finish, this is, as usual with Swampland, you make general predictions which then match with things that you already knew in string theory in concrete examples. So for instance, we already know in M theory, in 11 dimensions, there's something called the Orjava-Witten wall, which precisely looks like this. This is the 11-dimensional M theory vacuum. And at some point you find a boundary to it. And there's nothing in here. And on the world volume of this guy, there's interesting degrees of freedom living there, this E8 gauge fields. So the boundary of the universe can have interesting degrees of freedom. So I think this is a very exciting prediction of covariance conjecture. It's predicting that also for the standard model, you have something like the Orjava-Witten wall. So with that, I'll finish for today. Tomorrow, I will describe how to connect the covariance conjecture to string universality briefly, and we'll move on to the Festival anti-bound. So let me stop here and see if there's any questions. Thanks very much for the attention.
Thank you very much, Miguel, for the interesting talk. Okay, we have time for questions.
Can I ask a question?
Yeah, sure.
Please, please.
Are these the really unique ways of trivializing the cobordism? I mean, for example, what happens if you have one K3, then to kill it, just add a K3 with reverse orientation?
Oh, that is an excellent point. Yes. So what you are describing is, let me phrase what you're describing, removing the K3 part, because you're really asking a question about global symmetry in general. So suppose I tell you there's a particle with a global symmetry charge here, which has charge +1. Okay. This could be, for instance, your K3, but we don't have to think it's the K3. And so what you're proposing is, let's put another particle here with charge -1. So we could call it a K3 bar, K3 opposite orientation. And so once we do this, the total state has 0 charge and they can annihilate to the vacuum. That is certainly the case, but this happens also with any global symmetry. For any global symmetry, for any particle, you have an antiparticle. And if you consider configurations where the total charge vanishes, then there's no symmetry. Saying that a symmetry can be broken really means that if you just have this guy, the guy with charge +1, so if you remove this guy, still there's a process that can get rid of this charge. Okay, there's still a process that can, somehow turn this whole configuration into the vacuum. That's what it means breaking the symmetry. So what you were describing will work for any global charge, and it's not symmetry breaking. Did I answer your question?
Yes. So you say this is a sort of non-trivial way of killing the cobordism?
The one I'm describing is non-trivial way because it involves introduction of new geometries. The other one, the one that was being suggested before with the 2 particles, is a bit of a trivial way of killing. It doesn't really kill the global symmetry. Okay.
Okay. Thanks.
Any other questions?
Excuse me.
Yes, please.
I'm trying to see if I understood correctly. So in the last 2 minutes, about the standard model, are these objects that you described, like the Horowitz involved, the singularities that you mentioned, that we need to cancel the global symmetry for that topological invariant, or am I misled?
Yeah. Okay. So no, sorry, because I was a bit too quick here, okay? Because I was near the end. So let me explain a bit more carefully. So, right. So in general, when you have right. So when you have a global symmetry that is coming from cobordisms, okay? The defect that you need to introduce to kill the global charge has 1 dimension less. Okay, so for instance, here, if I compactify, if I have a 4-dimensional theory and I consider a class which has a 2-dimensional flux, like for instance the monopole, so I'm considering a configuration which has some non-zero integral of f, which is, for instance, the class I'm measuring here. The object that kills this, okay, the boundary of it has 1 dimension less. So it's a particle. And really the only thing I'm describing here is that a monopole carries magnetic flux, okay? Similarly, for this class, okay, this cobordism class has codimension 1, okay? So what we are saying here is that this has to do with the fact that I didn't describe that if you have a circle with periodic boundary conditions, you cannot shrink it to a point. So a normal circle, you can shrink to a point. You can just, make it very small and then disappear. But you cannot do it for a circle with periodic boundary conditions. So another way of saying this is that the boundary of a circle is a cigar, but if the circle has periodic boundary conditions, you need to put an object here. Okay. So because this has codimension 1, this will have codimension 2, and this is a string. It's dimension 1 plus 1. And the final case, 1 plus 1, and this is the spin defect I was describing here. And the final case, you can extrapolate a little bit, and go to the case where you look at cobordism group of charge 0. Of degree 0. What does that mean? That means a charge which is carried by all of space-time. So far, I've been describing charges that are carried by particles, by strings, by membranes, but you can keep going the logic, and you can imagine that all of space-time is carrying itself a charge, is carrying itself a conserved charge, okay? That's a global symmetry. If space-time itself carries a conserved charge, it's still a global symmetry, and it should be able to disappear. Okay, the cobordism conjecture tells you that the charge should be able to disappear. What does it mean that it's able to disappear? Well, it means that there is a defect for it. There's a boundary after which the space-time, which was carrying a global symmetry, is no more, and then the symmetry is broken. So this is the extreme application of cobordism conjecture. It's really telling you that every quantum gravity admits a boundary. And the idea is that these groups measure what is the charge that can be carried by space-time itself. So that's the new concept, I think. Even space-time itself can carry charges, can carry conserved charges, and we don't like that in quantum gravity. Did I answer your question?
Yes.
Or is it confusing?
Yes, no, yes, sir. Yes, thank you.
Okay, if there's any further questions and we don't have time now, please just send me an email. Okay, I did it yesterday and I did it the first day. I'm gonna do it again. I'm gonna write my email. Please write me an email with any questions you might have about any of these things. Okay.
Thank you very much, Miguel.
Thank you. Any other questions?
I don't see any other question.
All right.
So see you tomorrow.
Well then,
Final lecture.
thanks very much, and see you tomorrow. I'll try to have my computer fixed for tomorrow. Sorry about that.
No, thank you. Goodbye.
Bye-bye.
So we'll be back in 15 minutes.